We are in chapter 4 where we are discussing bending. This is the 21st session overall. Here we'll keep on discussing shear force and bending moment diagrams. This is a block diagram showing all the 36 sessions covered in the first 4 chapters. We are in the last session, which pertains to PM and SF diagrams only. After that, we'll look at the relationship between UDL, PM and SF diagrams, and following which we look at singularity functions. Shear force and bending moment diagram for individual loads acting on the same beam can be added up to give the shear force and bending moment diagram for composite loading. Here we have a beam subjected to 2 point loads. Now, due to load 1, this is the shear force diagram, and this is the bending moment diagram. Due to load 2, this is the shear force diagram, and this is the bending moment diagram. We can add these two diagrams to get a composite diagram, which is for this loading case. We can also add these two diagrams to get a composite bending moment diagram, which is for this loading case. We'll later look at how this can be done. We develop shear force and bending moment diagrams using a mechanical procedure. As such, it does not give much sense or feel of the diagrams. The process given here is suggested for personal use and is not part of any established method. Forming composite diagrams will help us with their familiarity, and we can anticipate diagrams or check them. Let us look at a second case where there are two different types of loads. So there's a point load acting here and a UDL acting. Due to the point load, this is the SF diagram, and due to the UDL, this is the SF diagram. This is the bending moment diagram due to the point load, and this is the bending moment diagram due to the UDL. We can add these two diagrams to get a composite shear force diagram for this whole loading. We can also add these two bending moment diagrams to get a composite bending moment diagram, again for this loading. We'll look at the process of adding using a similar case later. In order to form composite diagrams, we need to know the shear force and bending moment diagrams for individual loads. Here we have given a chart of shear force and bending moment diagrams for individual loads. We have differentiated into types of beams. So we have considered simple beam, cantilever, and overhang. We have then considered types of loads for each. So here we have a beam subjected to a point load. The shear force diagram will be as shown here. PA divided by L and PP divided by L are the reactions at the two ends. This is the shape of the bending moment diagram, and the maximum coordinate is PAP divided by L. Here we have the case of a moment acting on a simple beam. The shear force is then constant throughout the beam, and the magnitude is given as m0 divided by L. For the direction of moment chosen, the bending moment increases linear along B. Then there's a sudden drop in the bending moment diagram. After that, the bending moment increases till it reaches zero at a distance A from where the moment is acting. If the direction of the moment is opposite to this, then both these diagrams will be inverted. For a UDL, the reactions at the end are W0 L by 2. This is the shear force diagram. This is the shape of the bending moment diagram, and the maximum bending moment is W0 L square divided by 8. Here we have a point load acting on a cantilever at a distance A. The shear force will be constant for the distance A. The bending moment would be negative and increase linearly. It will be PA at the joint of the cantilever. Here we have a moment acting on a cantilever. It will cause no shear force. If the moment acts at a distance A, then the moment diagram will have a constant moment for that distance. Here we have a uniformly distributed load acting on a cantilever for a distance A. The shear force varies linearly, and the maximum shear force is W0A. The bending moment is in the negative region, varies in a quadratic fashion, and the maximum value is W0A squared divided by 2. Next, we look at overhangs. We consider loads only acting on the overhang and not in the intermediate span. This is because the intermediate span can be considered as a simple beam, and we can superimpose the shear force and the bending moment diagrams. So here we have a load P acting on the right overhang. This is the shear force diagram. On the left side, we'll have a force acting downwards. This is the bending moment diagram. It is negative and the maximum is PA. Here we have a point load acting on both the left and the right span. This is a possible shear force diagram and a bending moment diagram. We say possible because the actual diagram will depend upon the magnitude of the loads and the distances. The moment diagram, bending moment on both overhangs is linear, and the points at the supports are connected by a straight line. Here we have a UDL acting on both the left and the right overhang. This again is a shear force diagram and a bending moment diagram. That is one of the possible diagrams. The actual diagram will depend upon the magnitude of the load and the distance. In the bending moment diagram, on both the left and the right overhang, the variation is quadratic, and the moment that the supports are joined by a straight line. So now we have individual diagrams that we will use to form composite diagrams. Before one starts looking at composite shear force and bending moment diagrams, one should mention that they depend on the magnitude of the two loads. Shape configuration is not always unique. When there is positive shear force or bending moment for one load and a negative shear force or bending moment for another load for the same beam portion, then there can be alternate shape configurations. In our discussion, we mentioned about magnitudes in some cases, but not in all cases. Here, we have taken the problem that we discussed earlier by 2-point loads act on a beam. We'll look at the way shear force and bending moment are added. This is the shear force diagram for load 1, and this is the shear force diagram for load 2. Both for shear force and bending moment diagrams, we can follow a simple rule. When the shear force is positive in both cases, then we simply add them up. If the shear force is negative in both cases, then again we add the shear force in the negative region. If the shear force is positive in one diagram and negative in another diagram, then we subtract. Here between A and B, we add the shear force in the positive region. Between B and C, we subtract. So the shaded portion gives the shear force. Between C and D, we add the shear force in the negative region. These are the bending moment diagrams for load 1 and load 2. We leave the bending moment diagram of load 2 as it is. We take a section in A1, CP, which aligns with the maximum moment in A2. To the left of the section, we have ABCD, which we add to HF. And to the right, we have CDE, which we add to FI. Now, A1, B1, C1, D1 is not the same as ABCD. We only add the vertical ordinates. So CD here is equal to C1 D1 here, and L1 here is equal to L1 here. In this way, we get the composite bending moment diagram. We have also considered a case similar to this case. There is a difference, however. The load 1 here is considered to act in the middle. This is the shear force diagram for load 1, and this is the shear force diagram for load 2. Here the positive region can be directly added and the negative region also can be directly added. This is the bending moment diagram for the UDL, and this is the bending moment diagram of the point load. Here again we leave the second bending moment diagram as it is. We take a section CD in this diagram aligned with the maximum moment in the second diagram. We add the left portion to the left and the right portion to the right. The vertical ordinates are added as mentioned earlier. We can see that the bending moment diagram for UDL has the middle portion stretched in the composite diagram. Here we have a beam subjected to a UDL and a moment. The ultimate shear force diagram, that is the composite diagram, would depend on the magnitude of the moment and the shear force. So here we have drawn the shear force diagram for a chosen case. The shear force for the positive portion in this diagram will be added up, while for the rest the shear force will be subtracted. So in the end we get a smaller triangle in the negative region. Like shear force, the composite bending moment will depend upon the magnitudes, and we have chosen a particular case. Here we take a section CD, which is at the same point where the moment acts. We'll then add A1 to A3 and subtract A2 and A4. So if this is L1, then we have added L1 on top of. Here we have shown how we have subtracted A4 from A2, and this shaded portion is the result of the subtraction, whose vertical coordinates we have added here. In this case, we have a UDL acting on a small section of the beam and also a moment acting. The beam is a cantilever beam. The shear force is only due to the UDL acting. Due to the moment, the bending moment is constant for the portion till where the moment acts. This is the bending moment diagram for the UDL. Develop the composite bending moment diagram. We take a section CD and the portion left of CD is subtracted. We can see that UDL acting for a small distance behaves similar to a point load apart from where it is acting. So here for the portion it is acting, it is linear, but apart from that it behaves like a point load. Similarly here for the portion it is acting, it is quadratic, but the rest is similar to a point load. We now look at overhanging beams. As earlier mentioned, we'll consider the overhang portion separately and the simply supported portion separately. Here, there's a point load acting in the middle portion. The length of the left overhang is considered to be larger than the right overhang. Then this is the shear force diagram for the overhanging portion only. This is the shear force diagram for the middle simply supported portion. With the composite diagram, we realize that AB and BE is directly taken from the overhanging portion shear force diagram. The portion in between B and C gets added up and the portion between C and D gets subtracted. For the overhanging portion, this is the bending moment diagram. Since we have a UDL acting on the overhangs, the variation here is quadratic. Also, the variation here is quadratic. This is the bending moment diagram for the simply supported beam. The point load here is considered to be relatively high in magnitude, so that the length L1 is also relatively high. Here we have put together both this bending moment diagram. Notice that OMQ, the triangle, is not the same as this triangle. Only the vertical coordinates are the same. We mentioned that we consider L1 to be relatively high. That is why we have a positive portion and a negative portion in the bending moment diagram. If L1 is small, then the whole diagram can be in the negative region. The bending moment is given by AMNOPQE. That is the shaded portion. Now consider this overhanging beam. It has a UDL in the left overhang and a point load in the right overhang. The central simply supported portion has a UDL acting and a point load acting at half a distance. We consider the total UDL load to be larger than this point load and also half the distance of the left overhang greater than the distance of the point load right support. Then this would be the diagram for the overhanging beam. We earlier found the simply supported portion shear force diagram, but the simply supported beam was subjected to a UDL and a point load. So this is the diagram. Here we look at the composite diagram. Again, the portion AB and DE is directly taken from the overhanging shear force diagram. The portion BC is added up and the portion CD gets subtracted. This is the bending moment diagram, the overhanging portion. You notice that this portion has a linear variation, while this portion has a quadratic variation. That is because of the point load here. For the simply supported beam or the loading configuration, we found earlier that this was the bending moment diagram. Here we have formed the composite diagram by putting together these two diagrams. The portion MOQ is not the same as this. Only the vertical ordinates are the same. Again, depending upon the magnitude, this bending moment diagram can be totally in the negative region. The bending moment is given by AMNOPQE. Here we deal with a particular type of problem, that of minimum bending moment. We have a cantilever beam here with a hinge at B and a support at C. There's a uniformly distributed load of magnitude omega 0 acting throughout the length of the cantilever beam. We are required to find this dimension A, for which the bending moment will be minimum. Now, for bending moment to be minimum, the highest positive bending moment must equal the highest negative bending moment. As in a frame, here we'll separate BC and consider its equilibrium. Due to the hinge, there are two equal and opposite forces acting, one on BC and the other on AB. They are given here as RB1 and RB2. Considering equilibrium of BC, we can see that RB1 and RB2 would be omega 0 8 minus A divided by 2, which is also the magnitude of the reaction at C. The portion BC will be subjected to positive bending moment with the maximum as omega 0 8 minus A in bracket squared divided by 8. The cantilever beam AB is subjected to a negative moment at A. The negative moment is due to the omega 0 distributed load and also due to RP2, which is a point load. The maximum moment at A is therefore omega 0 A square by 2 plus RP2 into A, which is given here. We now equate the highest maximum positive moment with the highest negative moment. And here we cancel some terms and we end up with a quadratic equation of A. Solving the quadratic equation, we get A is equal to 1.373 meter. So if the hinge is at this distance, then the bending moment will be minimum. Here we have another example. This is a beam subjected to uniformly distributed load and a torque as shown. The uniformly distributed load is triangular in shape both in the left and the right portions. They create a couple which is resisted by the torque jacks in this connection. The total load here is omega 0 L divided by 2, which is also the total load on the left side. The resultant acts at a distance 2/3 L both on the right side and the left side. So the moment arm is 4L by 3. The force multiplied by the moment arm gives us the couple that acts. Due to equilibrium, the torque T will have the same magnitude. Now considering vertical forces, the vertical force that acts on this side and on this side are equal and opposite. So from equilibrium, we can see that there's no force acting at the connection at A. Now let us form the shear force diagram. If we take a section here, then we see that there's some shear force acting on the section. And if we move further from the left edge, the shear force increases till we reach A. So here we have shown an increase in shear force. Since the force here acting is downwards, the shear force is negative. Also, because this variation is linear, the variation of the shear force diagram is quadratic. As we go past A, the shear force decreases. It keeps on decreasing till we reach the right edge. So here we have shown the shear force decreasing till the right edge when it becomes 0. Now consider bending moment. If we take a section here, then there will be some bending moment. If we move away from the left, then the bending moment will keep on increasing till we reach A. Now this bending moment will be anti-clockwise and therefore negative. So we have drawn the bending moment in the negative region and it's shown as increasing. Since the shear force variation was quadratic, the bending moment variation would be UB. At A clockwise moment acts. So the bending moment jumps up from the negative region to the positive region. If we take a section here, then from the right side we see that the bending moment is positive. If we take a section further away, then the magnitude of the bending moment would increase and it is still positive. So we have drawn the bending moment diagram as shown.